Download this code from codegive.com, link in the description below. OK, let's talk about why you might want to hold off on establishing a rigid cleaning routine in your code, along with practical code examples demonstrating situations where premature or overly aggressive cleanup can be detrimental. Instead of immediately focusing on a routine, we'll focus on principles of resource management and how to handle cleanup gracefully and strategically when it makes sense. Why rush? The dangers of premature or rigid cleaning routines. The knee-jerk reaction of "I need to clean up everything immediately after I'm done with it" can sometimes be counterproductive. Here's why. 1. Premature optimization *. Like any optimization, cleaning routines should be driven by actual performance or resource issues, not just a theoretical fear. Spending time prematurely optimizing cleanup can lead to wasted development time *. You're focusing on a problem that might not exist or might not be the biggest bottleneck. Your time could be better spent on core functionality. Increased complexity *. Adding cleanup code increases the overall complexity of your program. More code means more potential bugs and more maintenance overhead. Reduced readability *. Interspersing cleanup logic throughout your core code can make it harder to understand the main flow of the program. Introducing bugs *. Cleanup done incorrectly can lead to dangling pointers, double-free errors, in languages that require manual memory management, or corrupted data. 2. Overcleaning *. Sometimes, cleaning up resources too early can actually hurt performance. For example, frequent allocation / deal location * constantly allocating and deallocating memory, or other resources, is an expensive operation. Reusing resources, example using a pool, is often more efficient. Premature cleaning forces you to reallocate unnecessarily. Cache thrashing * If you immediately release a resource that you'll soon need again, you might evict relevant data from caches, leading to slower performance when you reacquire the resource. Interfering with system optimization * The operating system or the runtime environment might be doing its own resource management, example garbage collection. Your manual cleanup might interfere with these optimizations. 3. Masking bugs * While cleanup is generally good, a rigid cleanup routine can inadvertently mask underlying bugs. For instance, if you have a memory leak and you diligently clean up the memory in a cleanup routine, you may never find the source of the leak, which could manifest in other, more subtle ways. It's better to address the root cause. 4. Tight coupling and inflexibility * A rigid cleaning routine can tightly couple different parts of your code. If you need to change how resources are used, you might have to rewrite the entire cleanup routine, potentially affecting many parts of your application. Principles of resource management, alternatives to rigid routines. Instead of blindly adopting a cleaning routine, focus on these principles. 1. Resource acquisition is initialization, RAII, especially in C++. RAII is a C++ technique, though the concept applies broadly, that ties the lifetime of a resource to the lifetime of an object. The resource is acquired in the object's constructor and released in the object's destructor. This guarantees cleanup, even if exceptions are thrown. 2. Defer cleanup to a higher level * Sometimes, the best approach is to defer cleanup to a higher level of the application or the operating system. For example, let the OS handle it *. If you're dealing with short-lived processes or threads, the OS will automatically reclaim resources when the process or thread exits. This is often sufficient for simple programs. Higher level abstractions * Use higher level abstractions, example database connection pools, message queues, that handle resource management internally. Garbage collection, GC in languages with GC, Java, Python, C, Go, the GC will automatically reclaim memory that is no longer reachable. Focus on avoiding memory leaks, example breaking circular references, and letting the GC do its job. 3. Measure and profile *. Never optimize without measuring. Use profiling tools to identify actual resource bottlenecks. Only add cleanup code if you have concrete evidence that it's needed and that it improves performance. 4. Design for testability *. Write your code in a way that makes it easy to test for resource leaks. Use memory leak detectors and other tools to verify that your code is behaving correctly. 5. Use try, finally, or equivalent, wisely * in languages with exception handling. Use try, finally, or similar constructs, to ensure that resources are released, even if an exception is thrown. However, don't overuse try, finally. RAII is often a better approach. 6. Use context managers. Python's with statement provides a convenient way to manage resources. The __enter___ method acquires the resource, and the __exit___ method releases it. 7. Manual memory management, C/C++. If using C/C++, carefully track resource ownership. Use smart pointers, std unique_ptr, std shared_ptr, to automatically manage memory. Avoid raw pointers and manual new/delete as much as possible. Code examples. Let's illustrate these points with some code examples in different languages. I'll focus on situations where premature cleanup can be problematic. Python, example, database connection pooling. Explanation, Python. *bad_example, * this function repeatedly opens and closes a database connection for each query. This is very inefficient because establishing a database connection is an expensive operation. The immediate cleanup, con.close, forces this overhead to be incurred repeatedly. *good_example, * this function opens the database connection once at the beginning and keeps it open for the duration of the loop. This amortizes the cost of connection establishment over many queries, resulting in significantly better performance. Cleanup is deferred until the end. *context_manager_example, * this illustrates how to use with to ensure proper resource management in Python. The database connection is automatically closed when the with block exits, regardless of any exceptions. This is the generally preferred Pythonic way. *timeit the timeit module measures the execution time of the functions to demonstrate the performance difference. You should see that good_example, and context_manager_example, are significantly faster than bad_example. C++, example, manual memory management versus smart pointers. Explanation, C++. *process data_manual, this function uses manual memory management with new and delete. The problem is that if an exception is thrown before the delete data line is reached, the memory will be leaked. While a try, catch block attempts to handle this, it's easy to make mistakes. This also has lots of boilerplate. *process data_smart pr, this function uses a std unique_ptr to manage the memory. The unique_ptr automatically releases the memory when it goes out of scope, regardless of whether an exception is thrown. This is much safer and cleaner. RAII in action. Key takeaways. * don't clean blindly. * avoid creating a cleaning routine just for the sake of it. Base your cleanup strategy on actual resource usage patterns and performance measurements. Understand resource management. Learn the principles of resource management, RAII, deferral, garbage collection. Asterisk prioritize readability. Asterisk strive for code that is clear, concise, and easy to understand. Don't sacrifice readability for the sake of premature optimization. Asterisk test thoroughly. Asterisk test your code for resource leaks and other errors. Asterisk let the system help. Asterisk take advantage of operating system and runtime environment features that can help you manage resources. Asterisk smart pointers. Asterisk learn them, love them, use them. Asterisk context managers. Asterisk great tool for Python for resource management. By focusing on these principles, you can write code that is more efficient, robust, and maintainable, without getting bogged down in unnecessary cleanup routines. Let the problems guide your solutions, and measure, measure, measure.